So we're just going to look at a few different examples of reactions and some characteristic types of reactions that we see in certain groups on the periodic table. All right, one type of reaction that we look at sometimes in the prep class, I don't know how extensively every prep instructor looks at these, but combustion reactions, where I have a reactant plus oxygen, and if my reactant is a hydrocarbon or an alcohol, my products are carbon dioxide and water vapor. Okay, so let's look at hexane and oxygen gas. So hexane, okay, hexane's one of our hydrocarbons. Now, if you on a straight chain alkane, all right, hexane, ane, it's an alkane. If you forget how to calculate or how to write the formula, you can calculate the number of hydrogens. So hex refers to 6. So I'm gonna have 6 carbons. Okay, so it's C6. Now, to get the number of hydrogens, okay, I'm going to do this formula. It's going to be 2n plus 2, where n equals number carbons. So for hexane, it's going to be 2 times 6 plus 2 equals 14. Okay, so C6H14. Okay. All right, and we're going to get oxygen. All right, and so we've got our hydrocarbons. We're going to get carbon dioxide and water. Now, these are usually done at very high temperatures, so we usually say water vapor. Okay, so now how do we balance this? Well, if we look at least for just a hydrocarbon, where we don't have oxygen in the first reactant, it's just there as the oxygen gas. Oxygen is written as O2, which means anything that we do to the water vapor needs to be an even number, because anything times 2 is an even number. And so if I put an odd number in front of the water vapor, I'm not going to be able to balance it. So it's H2, okay? Over here I have 14 hydrogens. Well, if I divide 14 by 2, I get 7. Which is an odd number, so I can't use that. So what I'm going to do is I'm going to put 14 over here, and I'll multiply this whole thing by 2. So now 2 times 14, 2 times 14, we're good there. All right, 2 times 6 is 12, so my carbon dioxide, I will get 12. Okay, so now let's figure out the oxygen. 12 times 2 is 24, plus 14 gives us 38. And 38 divided by 2 is 19. So there's a way that you can easily balance combustion reactions when you're just dealing with a hydrocarbon. Okay? All right, now we can look at some reactions of the alkali metals. I unfortunately do not have major samples of the alkali metals at home. You have to store them in mineral oil because they're very reactive in water, and I don't have like sodium and chlorine. So beneath this video on Canvas, there will be a supplemental video to this other YouTube video. But let's say I have something like sodium and chlorine. Well, if I take any of my alkali metals and one of the halogens, okay, so my group 7A, we can run a generic reaction. I'm going to do M is going to stand for metal, and X is going to be my halogen. Okay, so this is our generic form. Because all of our halogens exist as diatomics. Now, I did not put a state label next to my generic term for the halogen. Anybody know why? Because the halogens at room temperature are in different states. There's a couple that are gases, one that's a liquid, and one that's a solid. All right, and so I left the state label off that on purpose because my halogens can be in different states. Okay, all right, and so these are very vigorous. So if I have that sodium and chlorine, I'm going to make sodium chloride. There's a dude that owns a sample of every single element, and I watched a video one time, or I had a video on my iPad that I used to show one time where he made sodium chloride, like it was all poofing out in smoke, and he put a plate of spaghetti under it to just capture the salt. don't ever do that. If you make something, you should always purify it before you do anything with it, especially if you're going to eat it, which I don't recommend doing. All right. And then here's a generic reaction for our alkali metals with water. Again, these are really cool. They can be super violent, especially if you're dealing with the more reactive of the halogens. They're very exothermic, so they're pretty crazy. I've got a picture on the next page. All right, they look like that. And if you put some phenolphthalein in the water before you run the reaction, because the hydroxide ion is one of the products, it'll turn pink as you go because phenolphthalein indicates pink in the presence of a base. Okay? All right. So here we've got some halogens. So again, like I was saying, like different halogens are in different states. So chlorine naturally is a gas, bromine's a liquid. Bromine is one of 2 liquids that on the periodic table. Everything else at natural state is either a gas or a solid. Only bromine and mercury exist naturally as liquids. And so when I look at the halogens, you know, we can react with metals to form metal halides. We can react with hydrogen to form hydrogen halides. And then we can also make these interhalogen compounds when they react with each other. So those are a few of our representative reactions. The last thing we're going to look at is some specific reactions up in the atmosphere. That's in the next video.